Okay, so an HL extension about the pH scale is understanding that the self-ionization of water, the H2O splitting into H plus and OH minus, is actually temperature dependent. So that process of water splitting into H plus and OH minus is an endothermic process. You're breaking bonds, and the delta H for that reaction is 55.8 kilojoules per mole. So if we think about it in terms of equilibrium, what's going to happen when we increase the temperature of water? Well, when we increase the temperature in an equilibrium system, that should always favor the endothermic process. And in this case, the endothermic process is the forward process. So when we increase the temperature of water, it should split apart more than it does at room temperature. And what's that going to do to the value of Kw? Well, if H plus goes up and if OH minus goes up, both of these become bigger, then Kw should also go up. So the value of Kw will increase. However, we're going to see that increase as a decrease in the negative exponent. So I know that's rather confusing, but we're going to end up with an exponent probably to the minus 13, something like that. So some number to the minus 13. So it's an increase in Kw as both ion concentrations increase, right? So, and I guess it increases both of those. Okay, so here's the tricky thing. Increases both H plus and OH minus concentrations by the same factor. So what's really weird is that we're not going to make the water not neutral anymore. It's still going to be neutral water because we're still going to have equal concentrations of H plus and OH minus. What it does change, though, is that what is considered neutral pH is no longer 7. Let's take, for example, let's say it somehow shifted so far to the right that we had 1 times 10 to the minus 13 as the value of Kw. Well, if Kw equaled 10 to the minus 13, then as a result of that, H plus would equal 10 to the minus 6.5, and so would OH minus. They would both equal that. And so pH would equal 6.5, and pOH would also equal 6.5, and they would add up to 13, which would be the new exponent on the Kw. So that's an extreme case. I don't think neutral pH would ever really drop this low, down to 6.5, because the Kw wouldn't change all the way to 10 to the minus 13th. But the point is, as we shift more to the right and we increase those ion concentrations, just like we would expect if we weren't talking about temperature, as the hydrogen ion concentration goes up, pH will decrease. And as the OH minus concentration goes up, pOH will decrease. So now, because we're still having water, they're going to decrease by the exact same amount, and they're still going to be equal to each other, like if they were both equal to 7 in neutral water. So they're both equal to each other, just both be lower than 7. So it means that, so one trick is they try to trick you on this. Water is still neutral at higher or lower temperatures. Right? So that hasn't changed. The pH and pOH of neutral water is not 7 at temperatures other than 298 K. So that's the basics to know about this. The extension of this that I could see from the new syllabus is given some information about delta H, given some information maybe about delta G, they could give you a new temperature and have you try to figure out what is the new Kw value. That would be pretty extreme. I think they might just give you a new Kw value at this new temperature and then have you do solving for what is the new pH. So if they gave you a new Kw value, you would replace 10 to the minus 14th with the new value and take the square root of it, would give you the concentration of both H plus and OH minus. And taking the negative log base 10 of either one of those would give you the pH or the pOH. And I think that's about all they can do with this. But you should be aware that pH measurements really need to be taken at room temp at 298 because the pH scale is, or the values of pH of water are affected by changes in temperature because it's an equilibrium system.